In this video, we'll introduce a concept of work. We'll say exactly what it means for a body to do work. We'll define work and calculate work. We will also look at the relationship between work and energy. We will look at power and also efficiency. Now, when we first looked at energy, we said that energy is the ability to do work. So energy is the ability or the capacity to do work. And in order to do work, a body must possess energy, right? So let's talk about work. What exactly is work? Now, we say that basically work is done when a force acting on a body causes the body to move along the direction in which the force is acting. Right? So we say that work is done when a force acting on a body causes the body to move along the direction in which the force is acting, or we could say along the line of action of the force. Right? So what exactly does this mean? It basically means that in order for work to be done, a force must be acting and that force must produce motion. Right? So basically, if you push on an object and it moves in the direction of that force, that means work is being done on the object. However, if when the force is applied, the object doesn't move, then this basically means that no work is being done. Right? So again, for work to be done, a force has to produce motion. If the force is acting and the object on which it's acting doesn't move, then no work is done regardless of how large the force is. All right? So work done is equal to the force times the distance moved in the direction of the force. Right? So the work done is equal to the force times the distance moved in the direction of the force. Right? Now later on we'll see situations where a force is acting but a body is moving at right angles to the direction of the force. And in that particular case, then no work will be done. Right? However, in this case, we'll be focusing on situations in which a force is acting and an object is moving along the direction or along the line of action of the force, and therefore work is being done by that force on the body. So your symbol for work is typically W, and the symbol for force is F, and for distance or displacement, S. So the equation for calculating work done is equal to force times distance moved in the direction of the force, using the symbols W is equal to Fs. Now the SI unit of force is the Newton, and the SI unit of distance is the meter. So therefore it follows that the SI unit of force, of work rather, is the Newton meter. Right? So the SI unit of work is the Newton meter. But of course, when it comes to work, the Newton meter is equivalent to the joule. Right? So the Newton meter, when dealing with work, is equivalent to the joule. Right? Symbol for which is J. Now in physics, there is another quantity, another physical quantity, which has the same units, Newton meter, as work, and that is a moment of a force. But in that case, the Newton meter is not equated to the joule, only when it applies to work. Right? So the SI unit of work is the Newton meter, which of course is equivalent to the joule. And we will proceed to define the unit joule in terms of work being done, right? So we can say that 1 joule, 1 joule, symbol capital G, is the work done when a force of magnitude 1 Newton, or we could just say a 1 Newton force, right? So is the work done when a force of magnitude 1 Newton moves or causes a body to move a distance of 1 meter along its line of action, or along the direction of the force, or the line of action of the force, or in the direction of the force. Of 1 meter in the direction of the force. Right? So we can say that 1 joule is equivalent to 1 Newton times 1 meter. Alright? So 1 joule is the work done when a force of magnitude 1 Newton, or a 1 Newton force, causes a body to move a distance of 1 meter in the direction of the force, or in the line of action of the force, or along the line of action of the force. Right? So 1 joule is equivalent to 1 Newton meter, or 1 Newton times 1 meter. So let's look at a quick example of work being done. Calculate the work done on a box which moves a distance of 3 meters in the direction of a 4 Newton force which acts on it. Right? So calculate the work done on a box which moves the distance of 3 meters in the direction of a 4 Newton force which acts on it. So we'll simply write down the formula for calculating work. W is equal to Fs, and so W is equal to 4 newtons times 3 meters, and this gives us 12 joules. So the work done is equal to 12 joules, right? So far we've defined work. We'll state exactly what it means for work to be done, and we define the unit of work, the joule, and we've also done a quick example on calculating the work done by a force when the object on which is acting moves a certain distance in the direction of the force, right? Now let's talk a little bit about work. Now, what type of quantity is work? Work is actually a scalar quantity, right? So work is a scalar quantity, and therefore this means that work has only magnitude or direction, right? Oh, my bad. So work is a scalar quantity, which means that work has only magnitude but no direction, right? Now, if you look carefully, we see that work is obtained by multiplying force by distance moves in the direction. So if we talk about distance moved in the direction of a force, then this basically becomes the displacement. So force is a vector, displacement is a vector, but of course when you multiply them together, you get work, which is of course a scalar, right? Now, when we looked at energy, we said that of course energy is the ability to do work. And in order to do work, a body must possess energy. If a body possesses no energy, it can do no work. There is also um, the relationship between work and energy, in that whenever work is done on a body, then usually that body experiences an increase in energy, right? So usually whenever work is done on a body, its energy increases, right? So if work is being done on the body, then naturally its energy will increase. So we basically say that in order for a body to do work, it must possess energy. But if that body does work on another body, then that body on which work is done will have its energy increased. So for instance, if I want to do work by pushing this eraser, I must possess energy in order to do work. If I push the eraser and it moves, then I'm doing work and the energy of the eraser is increasing. In this particular case, because the eraser is moving, then its kinetic energy would increase, right? So we say that basically whenever work is done on a body, then usually the energy of that body will increase. If the body basically acquires some velocity, then its kinetic energy is increased. And if the body is lifted, say through some vertical height h, then the work done is equal to the increase in the potential energy of the body, right? So we could say that basically if when work is done on a body, its speed increases, then the work done is equal to the change in kinetic energy of the body, right? So if work is done on the body and the body's speed increases, then it means that basically work done is equal to the change in kinetic energy of the body, right? Similarly, if work is done and the object changes height, then it means that the work done is equal to the change in the gravitational potential energy of the body, right? So we say that if work is done in lifting a body through a certain height, then the work done is equal to the change in the gravitational potential energy of the body, right? So as I said before, there is a direct relationship between work and energy. In order for a body to do work, it must possess energy, and whenever work is done on a body, usually of course its energy will increase. So if work is done on a body and its speed increases, it means that the work done is equal to the change in the body's kinetic energy. If work is done on a body in lifting it through a vertical height, then the work done is equal to the change in the gravitational potential energy of the body. So let's look at a quick example. Calculate the work done by a force F on a body of mass m, or of mass 3 kilograms, which one moves from rests to a speed of 10 meters per second along the ground, and two, which is raised through a vertical height of 10 meters. Right? So let's look at these two questions. So they want us to calculate the work done by a force F on a body of mass 3 kilograms, which one moves from rest to a speed of 10 meters per second along the ground, and two is raised to a vertical height of 10 meters. Now, if you notice in this particular case, we're not given the magnitude of the work, of the force rather. And in the first case, we're not given the distance or how far the object moves. So therefore, we cannot use the typical formula for calculating work, which is to multiply the force by the distance moved. So we have to use the fact that the work done is equal to the change in the body's energy, in the first case, kinetic energy, and in the second case, the change in the gravitational potential energy. So in case one, we say that the work done, W, is equal to the change in kinetic energy, delta EK. So this triangle basically is a Greek letter, delta, which is used to mean change, right? So the work done or the change in. So the work done, W, is equal to delta EK, or the change in kinetic energy, right? And since the body was initially at rest, then that means its initial kinetic energy would be zero. And so therefore the change in kinetic energy is just the kinetic energy associated with this new speed. So the formula of kinetic energy, of course, is a half mv squared. But since we're dealing with change in kinetic energy, it would be the final kinetic energy in this case minus the initial kinetic energy, right? But as I said before, because the body was initially at rest, then its initial kinetic energy will be zero. So this gives us a half times 3 times 10 squared minus 0. So 10 squared, that's 100, times 3, 300, times a half, and this gives us 150 joules. So therefore 150 joules of work is done on the body in increasing its speed from 0 to 10 meters per second. Alright, so let's look at the second example. Again, in this case, we don't know the magnitude of the force F, even though, well, we're given the actual distance through which the bodies move, which is a vertical height h. And so in this case, the work done will be equal to the change in the gravitational potential energy of the body. So we can say that W for work is equal to delta EP. And so therefore W is equal to mg delta H, where of course delta H is the change in vertical height. So of course we're going to be taking G as 10, right? So taking G as 10, then we get that the work done, W, is equal to 3 times 10 times, what's the height? 10. And so this gives us 300 joules. So the work done by this particular force in raising the body of mass 3 kilograms through a vertical height of 10 meters is equal to 300 joules. All right, so let's now look at power. power. What is power? Power is basically the rate at which work is done. So power is the rate at which work is done, or the rate at which energy is converted. Right? So say power is the rate at which work is done, or the rate at which energy is converted. And as I said before, there is a direct relationship between work and energy. Whenever work is being done, it usually means that there is some transformation or some conversion of energy from one form into another. So therefore, power is the rate at which work is done, or the rate at which this energy transformation takes place. So the formula for calculating work is given by, power. So power is equal to work done or energy converted divided by time taken. Right? So power is equal to work done or energy converted divided by time taken, and using the symbols we can say that power is equal to W over T. Now many times the symbols for work and energy are used interchangeably, so sometimes you may see W for work, you may see W for energy as well, but of course in many cases you may see E for energy, so you could write or energy converted E over time taken. Right? Now the SI unit for work and energy is the joule, and the SI unit for time is the second, and therefore this follows that the SI unit of power, so the SI unit of power is the joule per second. Now the joule per second is one of those units which have a special name, and the joule per second is the same as the watt. So the symbol for watt is also a W, right? So the SI unit of power is a joule per second, which of course is equivalent to the watt. So instead of, let me just put, right, so the joule per second is equivalent to the watt, right? Now you should not be confusing the W for work with the W for watt, because one is a symbol for a physical quantity and the other is a symbol for a unit, and they usually appear on different sides of the equal sign. So for instance, if you see something like W equals, then this could never equal to watt, because this is actually representing a physical quantity. So if you see W equals, say, 5 joules, then clearly we're talking about work, and the work is equal to 5 joules. However, if you see something P equals 5W, then this W represents the watts, and of course P is the power, right? So power is work done or energy converted divided by time taken, whereas the SI unit of power is the joule per second, which is equivalent to the watt. So let's do a quick example. Calculate the power of a machine which converts 5,000 joules of energy in 5 minutes. And 2, a boy of mass 40 kilograms who runs up a flight of stairs. A flight of stairs, say 6 meters high in 30 seconds. Right? So let's do a quick calculation of power in these cases. So let's look at the first one. So they want us to calculate the power of a machine which converts 5,000 joules of energy in 5 minutes. So the formula, of course, is power is equal to energy converted divided by time taken. So the energy is given in joules, whereas the time is given in minutes rather. So we'll have to convert the time from minutes to second. So this is equal to 5,000 joules divided by, now 5 minutes, 60 seconds equals 1 minute. So 5 6s is 30. So this is divided by 300 seconds. Right? And so this gives us 50 divided by 3. That is 16.66. Let's just run it to 16.7 watts. Right? So the power of that machine would be 16.7 watts. Now in the second case, what we have is a boy of known mass running up a flight of stairs of a known height in a certain time. So the same formula would basically apply. So in this case, the power is equal to the work done, or the energy converted divided by the time taken. Right? So let's use work done. Now in this particular case, the boy is basically running up a flight of stairs of certain height, which means basically his gravitational potential energy is increasing. And so therefore the work done would be equal to the change in his gravitational potential energy. So we can say that W is equal to delta EP, right? And we calculate that using our formula, of course, mg delta H. So we calculate the work done. So this is equal to the boy's mass, which is 40 kilograms. And again, we take G as 10 and the height 6. And so this gives us 400. This gives us 2400 joules. Right? And therefore the power is equal to 2400 joules divided by 30 seconds. And this gives us 80 watts. So the boy develops a power of 80 joules per second, or 80 watts. Now the last thing we look at is efficiency. Now what is efficiency? Now basically, when we speak about machines, we're talking about devices which convert energy. So any device which converts energy can be regarded as a machine, right? So machines basically convert energy from one form into another. And what is really important is not the forms of energy between which are converted, but basically how efficient the machine is in converting this energy, right? So when we speak about efficiency, we're talking about basically the percentage of the useful energy, or the energy input, that is converted to useful energy output by the machine. Right? So, and in the case of work, efficiency basically is a measure of the amount of work, that is work input, that is converted to useful work output, right? So we see that efficiency is a measure of what we could say portion or percentage of energy or work input has been converted to useful energy or work output. Right? Now the word useful here is very important, because you know that basically in all energy conversion processes there will be some undesired form of energy, and therefore this will not be considered useful energy conversion. For instance, we know that basically that heat is often given off in many energy conversion processes, but the production of heat is not considered to be a useful form of energy conversion, but as a matter of fact, heat is generally regarded as wasted energy, right? So the formula for calculating efficiency, symbol for efficiency is E is equal to work or energy outputs divided by work or energy inputs, and this is times 100%, right? So we say that efficiency E is equal to work output divided by work input times 100%, right? Or it could be energy output divided by energy input times 100%. Now, can any machine be 100% efficient? In theory, but in practice, no machine or no energy conversion process is 100% efficient, right? Because for one, there's always some amount of energy which lost as heat, right? So basically, no machine or no energy conversion process is ever 100% efficient, because there's some amount of work always being done against friction, and this usually results in heat. A vehicle's engine, for instance, is not very efficient. As a matter of fact, the vast amount of energy that is actually extracted from the petrol or the fuel is normally wasted as heat,